Hey everyone, welcome back to the channel. Today we're diving deep into one of the most revolutionary concepts in artificial intelligence, transformers. And no, I'm not talking about Optimus Prime. By the end of this video, you'll understand how transformers work, what attention mechanisms are, and how models like BERT, RoBERTa, and GPT are built on this incredible architecture. So, if you're ready to demystify transformers, hit that like button and let's get started. So, what exactly is a transformer? A transformer is a deep learning architecture that was introduced in a groundbreaking 2017 paper titled "Attention is All You Need" by researchers at Google. The key innovation here was replacing traditional recurrent layers, like those used in RNNs and LSTMs, with something called self-attention mechanisms. The basic architecture consists of two main components, an encoder and a decoder. Think of it like this. Input text goes into the encoder, which processes and understands it. Then the decoder takes that understanding and generates output text. But here's why this was revolutionary. Unlike RNNs that process words one by one in sequence, transformers can process all words simultaneously. This means, number one, much faster training. Number two, better at capturing long-range dependencies, like understanding that "it" at the end of a long sentence refers to something mentioned way at the beginning. This parallel processing capability completely changed the game for natural language processing. Now, let's talk about the heart of transformers, the attention mechanism. Think about how you read a sentence. When you see the word "it," your brain automatically refers back to what "it" might mean based on context, right? For instance, the animal didn't cross the street because it was too tired. Your brain knows "it" refers to the animal, not the street. That's exactly what attention does for neural networks. The mathematical formula might look intimidating, but the concept is simple. Attention of query, key, and value equals softmax of query times key, transpose, divided by the square root of d, k, all multiplied by value. Here's what this means. Query, what am I looking for? Key, what information do I have? Value, what's the actual content? The model computes how much attention each word should pay to every other word. But wait, there's more. Transformers don't use just one attention mechanism. They use multi-head attention. Think of it like having multiple team members, each looking at the data from different perspectives. One head might focus on grammatical relationships, another on semantic meaning, another on contextual references. Typically, models use 8 to 12 attention heads working in parallel. This is what makes transformers so powerful at understanding nuanced language. Let me show you a concrete example of how attention works. Here we have a simple sentence, "The cat sat on the mat." This grid shows the attention scores between words. The brighter the color, the stronger the attention. Notice how cat pays strong attention to sat because they're the subject and verb, closely related. And on pays strong attention to mat because prepositions naturally connect to their objects. Each word attends strongly to itself, that's the diagonal line you see, but also learns which other words are important for understanding its meaning. This is how the model built a rich, contextual understanding of language. Now, here's a problem you might be wondering about. If transformers process all words simultaneously, how do they know the order of words? After all, "I love AI" and "AI love I" have completely different meanings, right? Without some way to encode position, these sentences would look identical to the model. That would be a disaster. Enter positional encoding. Positional encoding adds a unique pattern to each word's embedding based on its position in the sentence. The formula uses sine and cosine functions at different frequencies. Why sine and cosine? First, they create smooth, continuous patterns. Second, they allow the model to generalize to sequences longer than it saw during training. Third, they maintain relative position information. The model can learn that word A comes before word B, regardless of their absolute positions. Think of it like adding a fingerprint to each word that says, "I'm the first word" or "I'm the fifth word." This fingerprint gets added to the word's meaning, so the model knows both what the word is and where it appears. All right, Now that we understand the basics, let's look at one of the most famous transformer models, BERT. BERT stands for Bidirectional Encoder Representations from Transformers. That's a mouthful, so let's break it down. Bidirectional means BERT reads text in both directions, left to right and right to left simultaneously. This is huge because it means every word understands its complete context, not just what came before it. Encoder-only means BERT uses only the encoder part of the transformer architecture. It's designed for understanding tasks, not generation. BERT is trained using two clever techniques. Number 1, masked language modeling. Imagine you're reading "the cat blank on the mat." Your job is to fill in the blank. That's exactly what BERT learns. During training, 15% of words are randomly masked, and BERT has to predict them. Number 2, next sentence prediction. Given two sentences, BERT learns whether the second sentence naturally follows the first. This helps it understand relationships between sentences. Using BERT is incredibly simple with libraries like Hugging Face Transformers. Just a few lines of code, and you can load a pre-trained BERT model and start using it for your tasks. BERT excels at text classification, named entity recognition, question answering, and any task that requires deep text understanding. Now, BERT was amazing, but researchers at Facebook AI thought, can we make it even better? And that's how we got RoBERTa, which stands for Robustly Optimized BERT Approach. RoBERTa took BERT and turbocharged it with several key improvements. First, they removed the next sentence prediction task. Turns out, it wasn't helping much. Second, they trained on way more data. We're talking 160 gigabytes of text compared to BERT's 16 gigabytes. Third, they trained for longer with larger batch sizes. More data, more time, better results. Fourth, they used dynamic masking instead of static masking. This means the masked words change every epoch, so the model sees more variety. The results? RoBERTa consistently outperformed BERT across multiple benchmarks and became state-of-the-art for several NLP tasks. And just like BERT, using RoBERTa is super straightforward with the same Hugging Face Transformers library. Fun fact, the name RoBERTa is a play on words. It's like BERT's optimized cousin. Now, let's talk about the model that's probably most famous right now, GPT. GPT stands for Generative Pre-trained Transformer, and it's fundamentally different from BERT and RoBERTa. While BERT is bidirectional and encoder-only, GPT is unidirectional and decoder-only. What does unidirectional mean? GPT only reads text left to right one word at a time. It's designed to predict what comes next. Here's how GPT generates text. You give it a starting prompt like, once upon a, and then, step 1. It predicts the next word, let's say time. Step 2. Now it has once upon a time and predicts the next word, maybe there. Step 3, with once upon a time there, it predicts was. And this continues generating one word at a time, building on everything that came before it. This autoregressive approach makes GPT perfect for creative writing and storytelling, code completion, conversational AI, any task that you need to generate new text. The code example here shows you how you can use GPT-2 to generate text from a prompt. Modern versions like GPT-3 and GPT-4 follow the same principle, but with billions more parameters. This is the technology behind ChatGPT, which has taken the world by storm. Okay, so we've covered 3 major models. Let's put them side by side and see how they compare. Looking at architecture, BERT and RoBERTa both use encoder-only, while GPT uses decoder-only. For direction, BERT and RoBERTa are bidirectional. They see the whole context. GPT is unidirectional. It only looks backwards. Training tasks? BERT uses masked language modeling plus next sentence prediction. RoBERTa dropped the NSP task. GPT uses next word prediction. Here's the key takeaway. Use BERT or RoBERTa when you need to understand text, like classification, sentiment analysis, named entity recognition, or question answering. Use GPT when you need to generate text, like writing stories, completing sentences, or having conversations. RoBERTa generally performs better than BERT because of its more robust training, so if you're choosing between them, RoBERTa is usually the safer bet. But GPT serves a completely different purpose. It's not about which is better, it's about which is right for your task. All right, let's zoom out and see the big picture. How does everything we've learned fit together? Here's the complete transformer pipeline from start to finish. Step 1. Your input text gets tokenized, broken down into individual tokens that the model can understand. Step 2. Each token is converted to a word embedding, a dense vector representation. Then we add positional encoding to preserve word order. Step 3. This goes through multi-head self-attention layers, where words learn to pay attention to each other. Step 4. The output passes through feed-forward neural networks that further process the information. Step 5. Throughout the network, we use layer normalization and residual connections. These help with training stability and allow information to flow smoothly. Finally, step 6. We get output predictions, whether that's a classification label, a filled-in masked word, or the next word in a sequence. And here's a practical example using BERT for sentiment analysis with just a few lines of code. We create a classification pipeline, feed it text, and boom, we get a sentiment label with a confidence score. This is the power of pre-trained transformers. All that complex architecture we discussed is abstracted away, and you can use these powerful models with minimal code. Let's quickly recap everything we've learned in this visual summary. Key concepts. Attention mechanisms let models focus on relevant information. Multi-head attention provides multiple perspectives. Positional encoding preserves word order. And the encoder-decoder architecture determines whether a model understands or generates. Model strengths. BERT is your go-to for understanding tasks. RoBERTa is BERT, but more robust and better performing. GPT is unbeatable for text generation. Real-world applications. These models power modern search engines like Google, chatbots like ChatGPT and Claude, translation services, content generation tools, and sentiment analysis systems. The impact of transformers cannot be overstated. They've achieved state-of-the-art results across nearly every NLP task, enabled few-shot and zero-shot learning, and serve as the foundation for the AI assistants we use today. When that "attention is all you need" paper came out in 2017, nobody could have predicted just how transformative intended, this architecture would be. And that's it. You've officially demystified transformers. Let's recap the key takeaways. 1. Transformers use attention mechanisms to understand context by letting words focus on other relevant words. 2. Positional encoding is crucial for preserving word order in parallel processing. 3. BERT understands, GPT generates, and RoBERTa does understanding even better. 4. These models power the AI applications we use every day. I hope this video helped clarify how transformers work and why they're so important in modern AI. If you found this helpful, please give it a thumbs up. It really helps the channel. Drop a comment below if you have any questions or want me to dive deeper into any of these topics. Maybe a video on GPT-4 architecture or fine-tuning BERT? Let me know. And if you haven't already, hit that subscribe button and ring the bell so you don't miss future videos where we'll explore more cutting-edge AI concepts. Thanks so much for watching, and I'll see you in the next one. Happy learning!